some basic points we need to know about real analysis. Number one is the real line and its structure. Number two, function defined as mapping. And number three, countability of real number set. We term it as cardinality. These are the three basic things related with the concept of real analysis, which I would like to make clear in this video. First of all, the concept of mapping. Mapping is a rule. Mapping is a rule F which relates each member of the domain set to a member unique in the range set. So this rule have to be defined for each member of the domain set. That is very important. That is very important. When F maps A to B and we say that A is the domain set, then that rule F should be applicable to each and every member of this domain set. And they relates to unique images. Unique in the sense that we cannot map one element to two different elements in the range set. That means we cannot have two images of a single element, but it cannot be one to many, but it can be many to one. That means we have the image of this as well as the image of this as this, but we cannot have the image of a single element as any repeat element here. We must have a unique image of every element of the domain set. So this you should remember. And this F is 1, 1 and onto. What are the features of 1, 1 and onto? Whenever we have if A1 not equal to if A2, for A1 not being equal to A2, we have 1, 1 mapping. So for a function f to exist as its inverse, which maps if A to A, we must have this to be 1, 1, because otherwise we won't have unique image of every element. I hope this is clear to you. I would like to make it clear with this picture. Let us assume that three elements are there, A1, A2 and A3, and we have the image set here as FA, where A1 and A2 are mapped to a single element B, while A3 is mapped to B2. So this is not 1 1, because A1 is not equal to A2. They are distinct, but their images are same. So that is not 1 1. So whenever we introduce F inverse which maps FA to A, then we have multiple image of B1, isn't it so? F inverse B1 is A1 as well as A2. So it cannot happen, because each element must have a unique image for a mapping to be well defined. Now we move on to the concept of Cartesian product. Cartesian product. We all know that this representation of a point in this two-dimensional plane, in our coordinate geometry course we learned that xy means the coordinate of x and coordinate of y gives the unique position of the point P. Now if we have a set A having element A1, A2 dot 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 AN, and we have another element B as B1, B2 dot 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 Bn, then we have the Cartesian product of A cross B defined as A1 B1, comma A2 B2, comma A3 B3, and so on with AN Bn. Okay, so this is the definition of Cartesian product of two sets. Now if we relate it with this, we can easily apprehend and understand that if there are, say there are capital N number of points from 0 to, say this is capital M. So within this closed interval we have n number of points, and if we choose similarly an interval 0 to L on this y axis, we have, say here is n1 number of points and n2 number of points. So how many number of points are there in this? We can easily see that if these two are same, then we have same number of points, and that is called the cardinality of this set. So A has cardinality n, B has cardinality n, and A cross B, the Cartesian product, has the same cardinality. And in this respect, one should remember that the set of positive integers or natural numbers denoted as this is countably infinite. We know this. This go on, and this is termed as countably infinite. We all know that the set of rational numbers, which may be represented as this way, and this goes on. Everybody can realize that here we have 1 in the numerator, and in the denominator 1, 2, 3, 4 like this, and in the second row we have 2 in the numerator, while 1, 2, 3, 4 in the denominator. In the third row we have 3 in the numerator and 1, 2, 3, 4 in the denominator. And if we go by column, we can see that we have 1, 2, 3, 4 in the numerator, and in the denominator we have fixed 1, in the denominator, in the second column we have fixed 2. So that is the way of writing all the rational numbers. There is no rational number which is not written here. You can easily check it out, and you can also check that it can be counted, because they makes up 3. These 3 makes up 4 when we add these 2. These 4 numbers, 1 by 4, 2 by 3, 3 by 2, and here we have 4 by 1. So they all make up 5. And similarly, we have the other diagonal. So we can count all the rational numbers in this way, but you cannot count the set of irrational numbers, as they are uncountable. We all know that between every 2 rational number there is infinite number of irrational numbers. So they are not countable and termed uncountable. Okay? And the cardinality of this is usually denoted as aleph null. This is an Hebrew word. And the cardinality of the real number is termed as C. And actually it can be shown that 2 to the power aleph null is equal to C. So this much about the cardinality of all the sets of real numbers. So what is the cardinality? Cardinality is the number of elements in a set. And there is a famous theorem called Schroeder-Bernstein theorem. Schroeder-Bernstein theorem, which states that 2 sets x and y are said to be numerically equivalent. If we have a 1-1 and onto mapping from x to y, 1-1 and onto mapping. Obviously it is quite clear, since the cardinality of x, let us say that it is n. That means that we have n distinct elements in x. So if you have a 1-1 and onto mapping on to y, then we know that y is equal to f of x. That means the range set of the domain x engulfs or completes the y set, which is the image set of the domain x engulfs or completes the range set y. And since it is 1-1, so each and every unique element has a unique image here. So they have same cardinality, and so they are termed as numerically equivalent. So these are the concepts which we require to unravel the characteristics of real line. Another property is that equivalence class. Or equivalence relation. Actually, equivalence class is derived from the concept of equivalence relation. Now, just see that addition modulo 5. So, if any 2 integer is added, and if this addition is modulo addition with respect to an integer 5, then we have only 0, 1, 2, 3, 4 as a result. This is a binary operation. We add up 2 integers and then divide by 5 and take the remainder. So you can have only this much remainders if we divide any number with 5. And so the whole set of natural numbers is divided into 5 disjoint and separate set 0, 1, 2, 3, 4. They are disjoint and they exhaust the whole set of natural numbers, because there is no other result possible. So this is called equivalence class. And if we add up these 2 classes separately, let us add 0 and 4. So we get back the class 4, isn't it so? If we add them 2 and 3, that means all the numbers which give remainder 2 when divided by 5. Let us take an example. 12 is such number, and all the numbers which gives remainder 3 when divided with 5. So that is 13. Add them up and divide by 5. The remainder is 0. So they add up to give 0. Similarly, if we add 1 and 4, we again get back 0. And so they form a group. Can form a group. So these structures are related, interrelated. And another word which will finish this short video is regarding the concept of open set and closed set. Let us draw a sphere, circle, not sphere, a circle centered at a point, say 2, 2. This is a point C with coordinate 2, 2, and the radius is 1. So x minus 2 whole square plus y minus 2 whole square is equal to 1. So this equation represents all the points on the boundary of this circle, isn't it so? And if we put a symbol like this, x square minus 4x plus y square minus 4y, and this 4 and 4 adds up to 8, isn't it so? This 4 and 4 adds up to 8, and if we subtract 1 from it, it becomes 7, and here we have equal to 0. We make it less than 0, or we may make it greater than 0. Obviously less than 0 means all the points inside this circle. So if we put a strictly less than sign here, we have all the points which are inside the circle, not on the boundary, and these are the points on the boundary only. And this is an open set, and this is the set of all limit point of this open set, and if we add them 2, then it becomes the closed set, which includes its boundary. So this is a very important concept, pictorial concept, to understand the meaning of open and closed interval.